Good morning and welcome back to section 4 in chapter 2. In this section, we are going to look at how we can take the derivatives of the sine and cosine functions. We're not going to get into the other four trig functions quite yet. We'll see those later. We need a little bit more stuff before we can do those. But sine and cosine, we can definitely do. And this will also use the chain rule very heavily. So it'll be while we're learning sine and cosine, we're also going to be practicing chain rule. And so the derivatives of the sine and cosine functions, the best way of looking at them at the beginning is by looking at them graphically. So if we take the sine function graph, it looks like this. Now, when we think about the derivatives, remember back to the definition. The derivative is the tangent line, or it's the slope of the tangent line at certain points. So if we're looking at the slopes of these graphs, there are certain places where the slopes are fairly obvious. For instance, the maximums and minimums. What are the slopes of those tangent lines? The slopes of the tangent lines at maximums and minimums is 0. That's a very important idea that we are going to be doing a lot with in a couple sections when we're looking at applications of the derivative, because we're going to be able to maximize and minimize things by finding out where the derivative equals 0. So that's a very, very important idea here. But for us, it's going to help us graph the derivative. So we have those slopes. And then the other slopes we have are actually right at the steepest part of the sine and cosines, well, of the sine right now. We're looking at these angles, or these places right here. And it looks like the slopes of those places might be 1 or -1. And that's actually true. It is right at the steepest part of the sine and cosine graphs, the slope will be 1 or -1, whether it's going up or down. And notice in between the zeros, it'll either be going up or it'll be going down. It won't switch. So that means the graph of the derivative will either be positive or negative in between the zeros. So we can take those points that we've seen, we can graph those points. So starting out on the far left, a slope of 1, we're just going to graph a point at 1. Then we have a slope of 0, so we're going to graph the point at 0. A slope of -1, so we'll come down here and graph the point at -1. Slope of 0 again. Slope of 1 again. Slope of 0 again. Slope of -1 again. Another slope of 0. And then another slope of 1. So we have these points. Now we can connect them with a smooth curve, just kind of connecting the points, not making big jagged lines, because the slope is constantly changing in the sine graph. So the graph of the derivative, the graph of the slope, will also be constantly changing. So if we connect these graphs using a smooth line, we get something that looks kind of like that. That's pretty good drawing with my pen, right? Yeah, I'll take credit for that one. Actually, it was really nice lined up fade there. But we have this graph right here, which looks a lot like the sine graph, except it's been shifted over about pi over 2 units. Or this is also the graph of cosine of x. So the derivative of sine of x is cosine of x. It's like mind-blowing, but when you think about it, I mean, they're very similar, so it's not that bad. And so that's just by looking at the graph. We can actually show it algebraically. So looking at the proof of the derivative of sine, before we look at the actual proof, there's a couple limits that we're going to want to look at, so we don't have to do it in the middle of the proof. The first one is the limit as theta goes to 0 of sine of theta over theta. That's going to equal 1. Now we could prove this. It uses a squeeze theorem and a whole bunch of sectors of circles and stuff like that, where it's going to be in between two limits going to 1, so it has to go to 1. We could also look at the graph in the table, and in doing so, it's going to 1. We look at the table, everything says that should be 1, so we can believe that's going to 1. And the second one is the limit as theta goes to 0 of cosine of theta minus 1 over theta. That's actually going to go to 0. Same thing, we could look at the graph. Yeah, it looks like it's going to be 0. And then looking at the table, yeah, it makes sense that that would be 0. So we have the limit is sine of theta over theta equals 1. The limit as theta goes to 0 of cosine theta minus 1 over 0 equals theta. Now we can look at finding the derivative of sine using the definition. So using the definition, f prime of x equals h of x minus 0 of f of x plus h minus f of x over h. Remember, we can always go back to the definition to find these derivatives. We can plug these into the sine function. So we get the limit as h goes to 0 of sine of x plus h minus sine of x over h. The next thing we need to do is we need to expand out that sine of x plus h. Now we can't expand it like with a quadratic, but we can expand it using those angle addition formulas of sine that we looked at in chapter 0. Remember, sine of x plus h is going to be sine of x cosine h plus sine of h cosine x. Then the minus sign comes down, and h. We're going to group these sine of x's together and factor that sine of x out. So we have sine of x times cosine h minus 1, and then plus, that guy just went straight down there, over h. We can now split up the limit. The limit will split with the addition, so we can have the limit of this plus the limit of this. And then anything without an h in it can actually move out to the front because the h is the variable that we're looking at here. So we could rewrite our limit as this. And now this is where our other two limits come in. We have sine of x times the limit as h goes to 0 of cosine of h minus 1 over h. That's this guy. So this is just going to be 0 plus cosine of x times the limit as h goes to 0 of sine of x over h. That's that one. So this is just going to be 1. So we have sine of x times 0 plus cosine of x times 1. That's just cosine of x. So the derivative of sine of x is in fact cosine of x. That's what we saw by the graph. That's what we can see algebraically using the definition of derivative. And the derivative of cosine will actually be done very, very similarly to this. I'm not doing it for you because you're going to be doing it in your exercises, but it is very similar with the difference of the cosine addition formula is a little bit different, so that'll look a little bit different. But the steps other than that are basically the same. We can look at the graph of cosine, or look at the derivative by looking at the graph. So if we start out with the cosine graph, we can figure out where it's going to be 0. It's going to be 0 here, and here, and here, and here, and here. And then figure out where it's going to be 1 and negative 1, 1 and negative 1, and all those places. And so we can put our points. Let's see, the negative 1 goes down there. 0, 1, 0, negative 1, 0, 1, 0. So we can plot those points, then connect the dots. Hey, and that's a sine graph, almost. If we remember, the sine graph looks more like that. Ooh, that was yeah. This one, the derivative of cosine, is actually negative sine. So the derivative of sine is cosine. The derivative of cosine is negative sine. So they almost go back and forth with each other. And so here we have the two derivatives. Or in the general case, we use u's, and then we get the cosine u du, negative sine of u du. That's the chain rule in play there. So whatever we have on the inside, we'll have to multiply by the derivative on the outside. And whatever we have on the inside of the trig function will not change inside the trig function. That's the deal with the chain rule. You have the outside function of the inside function. So that won't change at all. If you're ever changing something inside the trig, you're doing it wrong. So let's take a look at some problems here. We can have just basic f of x equals sine of x, or equals 5 sine x. Because f of x equals sine of x is cosine x. That's way too boring. So f of x equals 5 sine x. The derivative, the 5 is a constant, follows the same rules as before. It's just going to stay out in front. So the derivative here is 5 times the derivative of sine of x, cosine x. That one's basically as easy as it gets. Looking at another one, f of x equals sine of 5x. This one's going to need chain rule. The only type that won't need chain rule is if you have a number times sine of x, or a number times cosine x. Everything else will need chain rule. So sine of 5x, the derivative, we're going to have sine of something. The derivative of sine of something is cosine something. So we have cosine of 5x times the derivative of the something. The derivative of 5x is 5. And I would rewrite that as 5 times cosine of 5x. Generally speaking, we like having that number in front so we don't think that it's inside the trig function. Let's move on to the next page. We have a couple more. Let's do f of x equals cosine squared of 3x. So first thing to realize here is cosine squared or sine squared could be rewritten. All that means is this is cosine of 3x squared. So now our chain rule, the big thing going on here, we have something squared. What's the derivative of something squared? That's a power rule. The derivative of something squared is just going to be 2 times that something. 2 times cosine of 3x times the derivative of that something. Well, that something's cosine of something. What's the derivative of cosine of something? It's negative sine of something. Negative sine of 3x times the derivative of the something. What's the derivative of the something? Something's 3x, derivative of 3x is 3. So we have 2 times cosine of 3x times negative sine of 3x times 3. I'd combine I'd multiply the constants together to get f prime of x equals, we have a negative 2 times 3, it's negative 6 cosine of 3x, sine of 3x. So that was cosine squared of 3x. What if we have cosine f of x equals cosine of x cubed? In this case, only the x is cubed. Notice the difference between the two. There's a reason why I'm showing you that, because that's a common mistake, misconception, whatever you want to call it. So in this case, only the x is cubed. So here the big function is cosine of something. What's the derivative of cosine of something? That's going to be negative sine of something, x cubed, times the derivative of something, 3x squared. So rewriting this, f prime of x equals negative 3x squared times the sine of x cubed. So notice lots of chain rule there. Pretty much every problem is going to be the chain rule. It's more practice with the chain rule in this section while getting the whole sine and cosine thing down. So that's what this section is about. Keep asking questions, keep working problems, and as always, happy mathing.